Week 7, problem 14. Two long wires hang vertically. Wire 1 carries an upward current of 2 amps. Wire 2, 20 meters to the right, and wire 1 carries a downward current of 4.5 amps. A third wire, wire number 3, is to be hung vertically and located such that when it carries a certain current, each wire experiences no net force. Alright, well, let's draw a picture and see where this goes. I think I'll use this guy. Oh, that looks straight enough. Stroke? Yeah. There we go. Ooh, I didn't know I had so many options. I go with black. Wire is supposed to be black. Unless they're copper colored. Or a handful of any other colors. Alright, there's one wire. There's two wires. And I'm going to... Yep, I'm just going to start going from here then. So, they said that what? 20 centimeters apart? That's terrible. There we go. These will be 0.2 meters. Okay. And let's see here. The magnetic field due to a wire. I'm just going to write up the magnetic field due to an infinite wire because I'm going to call these guys infinite. So it'll be mu naught I over 2 pi r. Normally I use the cosine theta plus cosine theta, but since it's infinite, we'll just skip that step. Okay, and then we need to know, they asked about the forces, so I'm going to say that use a fire incinerates little bunnies. F equals I L cross B. Okay, so now I'm just going to guess and check. If I put a wire, ooh, I can make it like a blue wire. That way it would stand out from the others. Yeah. Ooh, yeah, I like that. Alright. So, ooh, I could use little circles too. Wow, so exciting. Alright, I'm gonna use this circle. Ooh, that's good. That's good, I like that. So I'm gonna copy this guy, copy paste. Heck yeah. I'm gonna call this guy into the board. Or no, out of the board. This guy. Nope. There we go. They're adequate. Kind of adequate. Close enough. Alright. So, we want it to be, and we have, let's see, currents. Wire 1, this will be wire 1. And I'll be having a current upwards of 2. Okay? And this will be 2 amps. And this guy will be 4.5 amps and it'll be downwards. Okay. This will be 4.5. Alright. So, I'm going to start by placing the wire in the middle. So if I place this wire in the middle, this infinite wire is going to generate a magnetic, ooh, if I can group this, can I group this? Heck yeah, now it's a group. Haha, Shazam. Group. Oh yeah. Alright, so it's going to create a magnetic field so that, and I'm going to say it has a current going upwards. Let's can I do triangles? Heck yeah. There we go. Ooh, you gotta be red. Haha. I know it's not actually an accomplishment, but I'm gonna pretend like it is. Alright, so we got a current going upward, like that. It's gonna create a magnetic field going this way, like this. So then we're gonna have force over here. Ooh, actually what I'm gonna start with is, before I get too carried away, move this guy way over here. Ooh, yeah. So I'm going to find out what force these wires have on each other to start with. So this guy is going to create a magnetic field. Copy. Paste. Like so. This guy over here. Actually, I'm going to divide this into 3 sections here. We're going to have, I know I keep making this more and more complicated, but this is actually kind of, I think, a reasonably complicated problem. maybe? I don't know. Make him thinner. Ooh, dotted. Yes. And we'll go with black. You don't have to be this exact. Nope. With yours. Copy paste. Alright. So, this guy up here is going to be wire 1 in this region. Oh, 1. This region is going to be wire 2. This region is going to be wire 3. I'm just going to list the effects of the wires and see if somehow they can cancel each other out. Alright, so for wire 1, it's going to create an effect like this. So the magnetic field will be into the board here and here. I know you can't see when I'm touching the screen, but I'll pretend you can. And out of the board here. Alright, so then wire 2 is also going to be into the screen here. So it's going to be out of the screen here and here. Okay? So the effect of wire 1 on wire 2, we're going to have, so it's going to be V, which is the velocity of the particles in wire 2, the electrons, cross B. Did I do that wrong? Oh, I totally did that backwards. Why didn't you guys stop me? I know why, because you're, not actually here with me. Alright. There we go. And then wire 2. There we go. Like that. So wire 1, to make sure I got this right, into the board, out of the board. Wire 2, out of the board, into the board. Okay, there we go. Alright, so effect of the force on wire 2 from wire 1 is velocity of the electrons in wire 2 cross the direction of the magnetic field, so it's going to be to the right. There's going to be a force, and I'll do this guy in, I don't know, green? There we go. On green that doesn't look sickly. This is more of a jungle or nature green, as opposed to flu or stomach disease green. There we go. So that's the force on wire 1. Now we need to find the effect of 2 onto 1. So let's see. This guy is going to create magnetic field into the board like we showed. So velocity will be up into the board, so we got it pushing away. So these two wires are pushing each other away. Okay. Now I'm going to draw up the effect of 3 because the idea is we want everything to cancel out here. So we want 3 to be this direction and this direction. Okay. So, Nope, not what I wanted. Everything together. So if I put him in the middle like this, let's see what happens. Alright. Put him right there. Okay. So, if we have him like that, then we're also going to have, there we go, like that. And so for on this far wire here, wire 2, we're going to have V cross B. That works. We can do that. Yep. So the particle, the electrons are moving down, which is good. And then we cross the field. No, wait a second. Are those backwards? All right. Oh, no, I had these backwards. There's probably some rule to be learned here in life. And I am missing it. All right. Into the board, out of the board. There we go. There we go. All right. Up, up. Okay. So now, looking at wire 2, velocity going down, cross into the board. Nope, goes out. Goes out, which is not what we want. So this specifically will not work. Okay. Already failed. Alright, so let's move this guy over here and see if this works now. So now we have out of the board here, out of the board there. Okay? So we have, for wire 2, we have velocity coming down and magnetic field. Okay, that's good. That's good. We got that. Yeah, we got that. And then on the far side, we have V. Ooh, this might be good. Okay, so okay. So the magnetic field, due to our new wire 3, on wire 2, we have velocity going down of the particles, and we have B coming at, so we have a force to the left, which is good, is what we want, because it cancels out the other force. Alright, now for wire 1, we have velocity of particles going up, and the field coming out of the board, so we have a force to the right, which is also good. Alright, so we got the right direction for things. Now, we need to make sure that we can have the right magnitudes. So, we're going to have more effect. So what we want to do is we want to have the one with a higher current being, okay, so we have, it's going to depend on current and distance. So we want the one with a higher current to be the one that's further away, because we want it to balance out. We want one wire to have higher current and one wire to be closer. That way they can balance each other out. So if we have the wire over here, wire 3, it's going to be closer to the 4.5, and it's going to be closer to the 4.5. So 4.5 wire 2 will have both the advantage of distance and greater current, which is not what we want. So I'm going to try over here, see if we can get this to work over here. So, boom, 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 boom. We'll try the wire over here now. So, to the right will not work. Okay. So now, same idea. All right, put the wire over here. All right. So, look at wire 1. So we have V, voltage going up, and we have, let's see, is that into the board? Into the board, to the left. Nope, that's not going to work. Well, let's try this then. Let's just try reversing the direction of the current. There we go. So now, I'm going to do it this way. There we go. Okay, so let's try it this way then. So now, there we go. Wrap around this way. Now these are going to be out of the board, and this will be into the board. So now for wire 1 we have direction of current going up, out of the board. All right, we have to the left. It's good, or to the right. Okay. So now for wire 2 then we have current coming down, and we're coming out of the board. So we'll have force up. So these are correct now. So all right. So I'm confident, and now the wire is going to be closer to the weaker current, so the distance will allow it to have a same effect on both, possibly. Okay, maybe. Okay, so is this situation possible? Possibly. I'll wait till we do the math. Is it possible in more than one way? Well, we tried pretty much every single way, and only one of them worked. Possibly works. So describe the position of wire 3. Okay, so what we want is the total force to be 0. So we're going to have a magnetic field due to B3. So this is going to be due to the third wire right here. Oh, 3. That's due to the third wire. And then it's going to provide a force on each of the wires. And then it's going to be opposite directions. And I'm going to say that they are equal to each other. The magnitudes will be equal. So that's where I'm going to go with this. So I'm going to say that F1 equals F2. Really, it's just the magnitudes. They're F1 equals negative F2, but I'm not too worried about that. We'll worry about it later. So I can say that I1 L, which is infinite, but they're both infinite, so hopefully they'll cancel. Mu naught I over 2 pi R1. Yep. Equals, and that's describing the force on wire 1. Then for wire 2, we're going to have I2 L mu naught I, which is the current in, what is I? Oh, that's the current in wire number 3. Times 2 pi, and then R2, where R2 is going to be, I'm going to call it R1 plus 0.2, which is the 20 centimeters. Because the distance here, R1, what we're talking about here, is this distance plus that distance. There we go. Alright, so now I'm going to start doing some canceling. That way I won't have to do as much math. So the i's cancel. The mu naughts cancel. The l's cancel. I1 and I2 are different. The 2 pi's, yeah, I think those cancel too. So we are left with let's see, we're looking for R1, right? Yep. So I have I1 over I2 equals, nope, I'm going to do this differently. We have I1 times R1 plus 0.2 equals I2 R1. There we go. Now we're going to have to do some math. So we're going to have I1 R1 minus I2 R1 equals negative 0.2 I1. Okay? And then we're going to get R1 equals negative 0.2 I1 divided by, let's do I1 minus I2. Hopefully I2 is bigger, otherwise we're going to get a negative number and I'm going to panic. Alright, so I1 is 2. I1 is 2. And I1 is 2 and I2 is 4.5. Okay. So we're going to have negative, I'm going to say 2/5 because 0.2 is just 1/5 over 2 minus 4.5. Oh, and close enough. Okay. And 2/5 is just 0.4. Yep. So I'm going to do negative 0.4 divided by quantity 2 minus 4.5. Make sure 2 minus 4.5. Okay. And I got 0.16. That seems reasonable. 0.16. That'll be 0.16 meters. So what this is saying is that R1, which is this distance right here, is 0.16 meters. This is R1, and that is R1 plus 0.2. 0.2. There we go. Excellent. So describe position of 0.6. Direction. Left. It's on the left side. It's on the left of wire 1. Describe the magnitude and direction of the current in wire 3. Okay, so the current in wire 3 is this guy right here. So, oh, okay, we can just do that, find it right here. How do we find that? So we know what R can be. Maybe I can just use that? Oh, I don't know what the magnetic field is, though. That should be an easy way to do this. Maybe if I just zoom in and out enough times, it'll come to me. Maybe. Let's see here. F equals IL cross B. Okay, this is how I'm going to do this guy. So we know what the force is on wire 1, on wire 2, or wire 1, from the other wire. And we know that third wire has to cancel it out. So if I can find one of these, then I'm good. So I'm going to find effect of 1 onto 2. So I'm going to write this as, I'm going to do it up here, that way I can use some of the formulas I already have. So I'm going to call this the magnetic field of 2 from 1 equals mu naught I over 2 pi r. There we go. Therefore, the force, where this point r right here, is 0.2. Because it's 20 centimeters apart. So I'm going to say that the force then, and the current from wire 1 is 2. That's 2 amps. So to simplify, I'm going to say that we have mu naught times 2 over 2 times 2, 0.2 is would be 0.4 pi. Okay. I can probably simplify that a little bit more. So mu naught over 0.2 pi. Okay, I'm good with that. So that's the magnetic field. So then we gotta find the force, which will equal, and this will be the force on 2 from 1, which is ILB, fire incinerates little bunnies. So we have what, 4.5? 4.5. So we have 4.5 L times the magnetic field, which is mu naught over 0.2 pi. Alright? And this has to equal the force on wire 2 from wire 3. It's actually negative, but I'm just not going to worry about the negative right now. So this will be ILB again. So we're going to have, again, 4.5 amps in wire 2. Going to still have an L. Now we need to find the magnetic field from wire 3. Magnetic field from wire 3 will be, let's see, mu naught. Ooh, we just had that written down, didn't we? Yeah, I'm sure we did. Excellent. Will be right here. The magnetic field from B. I should probably just figure it out again. So the magnetic field from 3 is mu naught I over 2 pi r. Which in this case, I is what we're looking for. That's the question. And R is going to be, we had 16 centimeters, so it'll be 16 centimeters plus 20 centimeters, which will be 0.36 meters. So it'll be mu naught I over 2 pi times 0.36. And put a little times here. Okay, got it. So now, can I just... that is so lazy of me. Actually, I'm gonna do it this way. Nope. Nope. Just straight up move. Bam! Heck yeah. Nope, got the little tail for the Mew. There we go. And I'm gonna pretend this guy never existed. Nope, and I just lost the tail. That's okay. Alright. So now, I'm gonna set this equal to that. Oh, terrible boardsmanship. But I'm gonna do it anyway. Nope. Oh no, I didn't want to bring that back. Delete. Delete. Nope. Just want to get rid of this portion right there. Delete. And delete. Alright. So get some blue for some contrast. And we'll start canceling. Oh, you die. You die. You're not. You go 2. I'll be left. You get rid of the pies. I'll leave 2, so that way I don't get too confused. Alright. So then rearranging, we're going to have I equals 2 times 0.36 over 0.2, which will be 0.7. Yeah, I'm just going to Wolfram it. 2 times 0.36 divided by 0.2. 3.6. That even seems reasonable. Equals 3.6 amps. Alright, so if you're a little confused about where I went with that guy, so the whole concept that I went with was wire 1 is going to create a force on wire 2. And that's going to be F equals IL across B, where B is found using your infinite wire formula. Well, we know that that force is then going to be exactly opposite of the force that 3 creates. So you can set them equal to each other, and the only unknown you're going to have is this I which is the current of wire 3. Then when you solve for that, then you have the current in wire 3. And what is it, 3.6? Such a round number. Yeah, quite round. 3.6. Nice. So then we know we're going to have 3.6 amps in the down direction. Right. And that's how I would approach this one. This one was pretty hefty. That's good. They really ramped this up. Man, they keep the 15 and 16 are even harder. Quite the adventure. Oh, probably should answer the first 2 questions too. Is this possible? Yes, because we just did it. Is it possible more than one way? I don't think so. I think there's pretty much one way, which is why they ask such specific questions there. Alright, on to number 15. Hope this guy helped. If this helped you out a little bit, hit the little like button. Helps me out. Alright, take care. See you on number